Hi there, welcome to Chapter 3.4 from Stevens' Matrices, Vectors, and 3D Math. In this chapter we're going to talk about Eulers Method. It is pronounced Euler, as in someone who's drilling for oil. Mathematicians prefer the appropriate pronunciation on that, so as much as you'd like to say Eulers Method, if you say Eulers, you'll be ahead of the game. Okay, so we're going to put this into full screen mode before we start talking about Eulers Method. Okay, so what I want to do, I'm going to go back to Chapter 3.3. And back there, we derived this function, which was the position for a projectile in motion, right? And it has something to do with the launch angles and the initial velocity, and then the height had to do with the acceleration due to gravity, right? The gravity constant. And if we took that derivative, actually the way we derived it was we started at acceleration and moved back to our position. But if you start at position and start differentiating, take the derivative, you get velocity, and if you differentiate velocity, you get the acceleration. But what we're going to do here in Euler's method is we're going to say, all right, I want to know where this thing is at all times, but I'm not going to use this function. I don't want to use that. What I'm going to do is say, if I know where this position is at one time, suppose I know its position is right there where I drew that red dot, and I know its velocity looks like that, then I know at the next time step that that projectile is going to follow that velocity vector, right? And so that's the whole idea with Euler's method, is how do we accurately and efficiently follow the velocity vector to just keep updating our position so that we don't need to know where the projectile is at all time, right? This is the function for all time. We just want to know, if we know where it is now, where will it be next? So that's the game of Euler's method, and of course there's a little bit of math involved because we want to do it efficiently. And so it's this one step at a time approach to moving through 2D and 3D. Now, it's derived fairly simply by this. If you take our position function, right, and I differentiate it, I get the velocity function. Right? But if you take this position function and use the formal definition of the derivative, you get this, right? That's the formal definition. It's the limit as this variable delta t goes to 0, r plus delta t minus r of t over delta t, right? It's a slope of the tangent line if we were to graph it in t. But what we're going to do is we're going to just look at this part right here. We're going to say, all right, if delta t is small, and this is critical, then this equal sign is no longer valid, but it's approximately equal to. And so I just stick an approximately equal to, and I say, all right, I'm going to assume that delta t is small. And now I'm going to solve this equation, or this approximate equal to, right there. I'm going to solve it for this term, the r of t plus delta t. And that's the magic, so I multiply both sides by delta t, and then I can add r of t to both sides. But the important thing is that I can get r of t plus delta t. What that means is that I have the position in the next time step as a function of the position where it currently is at time t, plus the time step times my velocity at this particular time. Right? So I'm just moving forward by delta t. Moving forward by delta t. That's how I move through my time. All right? And my space in this case, or 2D or 3D. So here's how this is the way this works, right? Suppose I know where my position, where my particle or projectile starts, right? I'm going to know where that is. And I'm going to use this tilde notation to represent the Euler approximation. Now, at time 0, this is actually, there's no error here, right? It is actually known. But then at the next time, delta t, and I'm going to make sure that delta t is small, right? That was critical. Then my position, or the approximate position, at this next time step is going to be where I was at the current time, which is time 0, plus delta t times my velocity at time 0. So I'm getting r of delta t just from stuff that I already have up here at 0. And then if I want to find r of 2 delta t, I just go another delta t, right, another time step. Then it's going to be where I was plus delta t times the velocity of where I was. Then if I want to get to 3 time steps, it's where I was at 2 time steps ago. Or not 2 time steps ago, but at time 2 time steps. So it's where I was times the time step times velocity at where I was. And you just keep going and on, and you can get this formula right here. Right? But it's not really a formula. You actually march through it until you're done marching through it. So it's not really a formula per se as the original function for all time. You got to remember, keep delta t small, because what's going to happen is that this is an approximation, right? And then you use that approximation and make another approximation. So not only is there some error in, say, this second approximation right here, but there was error on the stuff you put in there in the first place. So that's what's called compounding error or propagated error. And so you're going to get some error, but if delta t is small, that error is minimal, right? And you'll get to see an example of that in a second. All right, so let's go on to the next page. We'll do our example in 2D. We're going to do the example we actually did in chapter 3.3. We have a ball that's kicked with an angle of elevation of 30 degrees. This is just in 2D. And so we have a 30-degree angle of elevation and an initial velocity of 80 feet per second. All right. And we're going to try to track this ball through 2D. We're going to use time steps of 0.5 seconds. Right? And so if this is our position function, then if we differentiate that, we get our velocity. So we'll actually get our position function, or get our position from our velocity function, right, which looks just like this. 40 root 3 for x, and y is 40 minus 32t. In this case, y is the height, so it's being dragged down by gravity. All right, and it's starting at 0, 0, so my initial approximation, my position at time 0, is just 0, 0, right? That's, if this is x, this is y, 0, 0. Then at the first time step, where delta t is 0.5, right? That's why my first time step is 0.5. I take where I was, plus 0.5, that's my delta t, times the velocity at time 0. So I get that from there, right? And I get these values here. Those are numerical values. And so once I have my position at 0.5, my approximate position at 0.5, I can get my position at time equals 0.1, or not 0.1, but positive 1. And that's going to be my position at 0.5, which I got right there, plus my time step times my velocity at 0.5. And I get these numbers. So again, these numbers represent x and y. X, y. All right, so you can see x and y are indeed increasing. Then I can get my third time step, which is 1.5 seconds. I take where I was at 1 second, add my delta t, or my 0.5, times where my velocity from back then. All right? And I get an x and a y at time 1.5. And I keep going. And when we did this problem by hand, we noticed that it actually hits the ground. Or not by hand, but when we used the r of t that was valid for all t, we said t star is 2.5. That's when it hit the ground. So that's why we're stopping at 2.5. And so here's the thing. If you plot it, these black dots here, so this is that same trajectory. The black dots here are the exact solution, right? So this is the exact and it was found in the last chapter, chapter 3.3, found by the vector valued function r of t. But these red dots here that I'm circling now, those are coming from my Euler approximation, right there. So these are the approximations. And as you can see, it's not a very good approximation, right? And as time proceeds, my error gets greater, right? Initially, I have no error. You can't see the red dot. That's because it's behind the black dot. But first I get this error. That's not so good. It's off by like 5 feet. You get this error, even bigger. This error, even bigger. This error, even bigger. And so the errors are getting bigger and bigger as I proceed. But that's because I took a time step that, while it seems pretty small, 0.5, a half a second is actually a pretty big time step. And so on the next page, what you'll see is the comparison, a similar graph as delta t gets smaller. So on that previous page, delta t, my time step was 0.5, right? And it looked pretty bad. Now if I make delta t 0.1, you get a lot more time steps, right? You've got to still cover 2.5 seconds. But the error is not nearly as big. In fact, this chunk of the error is really small. But then it sort of picks up and you get some error more, a little bit more every time, right? But if you crank it back, if you cut that in half to delta t equals 0.05, now things are really starting to look close. Right? Certainly close enough that you wouldn't notice as a casual observer. Now, if you were working for NASA or something, you'd need it to be a lot more accurate than this. But if we're just sort of visualizing bouncing around in 2D, a time step of 0.05 is actually pretty good. And so how do we do that with MATLAB? So this is basically how I created this code, was used to create these graphs, right? And so here is my initial position. I'm starting at x equals 0, y equals 0. That's my initial speed, 80 feet per second. This is that angle of elevation in degrees, right, whenever I set theta. And then I convert it to radians because that's what the cosine function takes, and the sine function. And let's see, what else do we have? This is whenever I'm going to end, t equals 2.5. And I'll do a time step. So this particular code corresponds to this graph because the delta t equals 0.1. And then the number of time steps I'm actually going to take, t steps, that's the number of time steps. That's just how long divided by how big of a step, right? So it's 2.5 divided by 0.1. So 25. It's going to be 25 time steps to get from here to there. Okay. And then the actual t is going to be my true. Now, so this part is the exact solution. This is the exact. This is the stuff in black up here, right? And it doesn't. The black curve is the same for both of these graphs and the one before it. So I first go from, I let t go from 0 to 2.5. And then here's my x and y, and then I just plot it with my dashed line, right? And then I'm going to plot the original, this first point with a black dot. So I plot that point with the black dot, right? And I fix my axes. And so here's actually the Euler approximation. This is, I'm marching through time, right? Marching through time. And I'm going to go this many time steps, so it's a for loop. I know I have this many time steps. And I do have my velocity function here. And this is my approximate. That's that r tilde of whatever delta t I happen to be, right? So tilde r1 is going to be where so the position r1, that's the r tilde of t plus delta t. That's what I'm going to call the r1, right? r1. And it's a function of tilde r0. That was just the r tilde of t. So that's basically the first one. So this is the original. Let me do it up here. This is the original point. And then this is the next point. And notice the next point is just equal to the original point plus delta t times my velocity. And then I plot it, and my t, my value of time increases by delta t. And then I'm this plotting the capital R1. This is actually the exact answer, right? It's not. It's come from right here. Let me show you where that is. This is that exact right there. So this is what's drawing those black dots. I'm not sure where this black line is. All right, I think it's x exact, y exact. Oh yeah, you can see it's this little line here. Right. But the big black dots come from here. So I'm plotting the exact solution in black dots and the approximate with the red dots. So this is called Euler2D.m. It's in the Chapter 3 program repository. You should take it out, play around with it. I don't have MATLAB on this particular machine. And just play around with, say, things like changing delta t here from 0.1, maybe make it 0.5 and then cut it down to 0.01 and see what happens. But what you should notice, unless you get crazy small, is that when you decrease delta t, all right, delta t gets smaller, the accuracy will increase, but you will have to take a lot more steps, right? So you want to find this balance between accuracy and number of steps. And actually, if you take too many steps, then you start running into other problems as well. So you want a reasonable delta t so that you can get where you need to go in a decent amount of time. You sort of want it to be as big as you can within a tolerance of accuracy that you're willing to accept. But the weird thing here, and I don't know if you've noticed this, as we were talking, we said, oh, we can find the position at any, or the approximate position, and all we need to know is the velocity. But the problem is that if we knew the velocity, right, we used this right here. That was our velocity function. And so we avoided using the position function, but we still needed the velocity function, which is just about as complicated, so we're not really saving ourselves all that much effort. But what is nice is that then we can update in the case, let me give you a little preview first. In the case of constant acceleration, we can update the velocity function with the acceleration function, right? Just like we did position, right? Eulers method, we estimated, let me see, we estimated the position. We estimated position from velocity. And what we're going to do here, right? So that's what we did up there. We estimated the position with the velocity. But now what we're going to do here is we're going to estimate the velocity from the acceleration. And the wonderful thing about that is that, and so it goes like this, acceleration is the derivative of the velocity. And so if I let delta t just be small, then this becomes an approximation sign, and this goes away, and we're left with this. And then we can get our velocity at our next time in terms of our velocity from the current time plus delta t times the acceleration at my current time. But now the nice thing is, if my acceleration is constant, then that doesn't change at all, and this relationship here is actually an equal to sign. So my approximation becomes exact if I'm assuming a constant acceleration, and I just update my velocity with my acceleration. And that's great. And so what that means is if you go all the way through this same thing, your Newton or your Euler's approximation, you don't have to use, notice there is no need for velocity. That velocity function is gone. all I have is my acceleration function, which is, well, there's my acceleration due to gravity, right? And there's my acceleration vector valued function. Really easy. 0, negative g. You're always accelerating down with the force of gravity. And so my new position is taken from my old position plus delta t times my velocity. So then I plot it, and then I update my velocity. My new velocity is just my old velocity plus delta t times my acceleration. And look how short and easy this is. This is the Euler approximation marching through time. It's 3 lines of code. Now I shortened it from the previous example because in the previous example I had a R1 right here, and I updated R0 and R1. Here I'm not using R1s and R0s. I'm just using R, right? So in this position, this is sort of the new R, this is the old R, but there's really no reason to name them anything else. So I'm updating R and dumping the old value. So look at that, that's amazing. It is a total of 3 lines of code inside my for loop that allows me to move through 2-dimensional space in the case of a projectile with constant acceleration. And all I do is update my velocity with that function right here. But remember, to do that, for this equal sign to be valid, my acceleration has to be constant. But if my acceleration isn't constant, I can still use this to update my velocity. It's just then I'd get some error. There would be an approximation along the way. And I believe that wraps up this chapter. Right? In the next chapter, we'll take Eulers Method right here, and we will start bouncing around in 2 space. In other words, once we go up, once our projectile comes up, and then we realize that it hits the ground, we're going to do the collision detection and then a bounce, and we'll just take right back off. And we can bounce around in 2D. That's great stuff. But we're good for now. Chapter 3.4. We're finished. Bye now.